Now, our destruction RBD simulation, with this extra debris layer added, is looking quite cool, but we really need to add a volumetric dust pass to this in order for it to really look nice and realistic. And to start out our dust sourcing, we can actually start out with our debris setup here. In the debris setup, we brought in our rendered geometry, got rid of the tiny pieces there, and then on the larger ones, we unpacked that geometry and then isolated all of the inside faces, and then just scattered tons of points on those inside faces. And then after generating this dense point scatter on those inside faces, we used our RBD simulation transform points to apply that sim animation to those scattered points there, and we've calculated their speed, creating the speed attribute based on velocity, and then we deleted out the slow moving pieces. And then to optimize this a bit more, we brought in the environment and scaled that down to the sim scale, used that to group the points that are below the ground, and then blast away those points that are below. So this gives us a good starting point that we can use to set up our dust sourcing. So I'm going to copy this entire section here from that object merge down through where we're blasting away the stuff below the ground. I'm not going to worry about this kill percentage and such because that's a bit more specific to the debris sourcing. We're not going to use that for the dust sourcing. And then back at the object context, I've set up a fresh dust geometry object. Let's dive inside there and paste in the source. And most of this I'm going to keep the same as how we've set it up for the debris. One thing that I'm going to do slightly differently is just pick a different speed cutoff because I do want some of the slow moving pieces to still have some dust coming off of them. So I'm just going to change the speed threshold here a bit. So I'll just select the speed calculation and the blast based on that, disconnect those. And this reordering doesn't really matter, it's just sort of a personal preference thing. And I'll select the rest of this network here that we copied over, set a net box on that. I'll call this sourcing based on debris setup, and then attach our speed-based calling after that. So if we display this blast here, you can see that's removing a bunch of the slow-moving pieces down near the ground here. And we can tweak this speed cutoff to our liking. I'm going to try just a very low speed value, something like 0.03. So this will only remove the points that are moving extremely slowly. It's not quite as aggressive of a speed threshold as we had for the debris. And now we can take all of these points and we can extrapolate them backwards to their previous position so that we can build a seamless volume source between frames. And it's really one of the classic problems with volumetric simulations. If you just source from pieces that are moving across the scene here, then you'll just get spots of those sources appearing in your simulation. And we really want those sources to always be smooth and filling up all of the space in between each frame position. So my favorite way of addressing this is to extrapolate these points backwards based on their velocity and construct some lines from that extrapolated back position to their current position. So to extrapolate those back based on velocity, let's drop in an attribute wrangle here, and we'll take the current point position and say minus equals to subtract the value of the velocity, but the velocity is a units per second value. So on each individual frame, we don't want this to be extrapolated back by the amount of space that it would cover in a second. We want it to be extrapolated back the amount of space it would cover in one frame. So multiply the velocity by the time increment, which is a standard Houdini variable that's just available by default in these wrangles. And then if you display this point wrangle, you can see this is pushing those points backwards a bit. And let's rename this wrangle extrapolate backwards. And then we can merge this with the current frame position. So just wire the blast and that extrapolated position into this merge, and we can now create polylines between these points. So let's drop in an add SOP after merging those points together. And on the Polygons tab, let's go to By Group and add based on an attribute. And we currently don't have an ID attribute that we can use to match up points from the current frame to the previous frame. So we should add an index to this. And generally you want to add these index or ID attributes when things are in their rest position before they start moving, just so that you can guarantee that these values aren't going to change. So if we go back to our scatter before we applied the simulation animation to this, then just after this scatter, let's drop in an enumerate SOP. And the enumerate is just going to set an ID value on all of the primitives or points. It's defaulting to primitives, so let's change it to points, since we're just scattering a point cloud here. And if you look at the spreadsheet, you can see it's creating this index attribute, and these index values are just matching the point numbers. So this is useful when we merge together two different sets of our points here. So we have the current frame position, and we have the previous frame position. So when we merge those together, we now have this consistent index attributes between both sets of points. So on the add SOP, under attribute name, type in index and display that. And you can see it's now creating lines from the current position to where it's extrapolated back based on velocity. So this is already looking pretty cool. And now let's add some noise to this so that we don't get these perfectly straight streaks here. But when we add these polylines with that add SOP, we're not really getting any resolution in the middle of these lines. If you turn on the point display, it might be a bit hard to see, but we're essentially just getting a start and end point here. So if we want to noise this up, we need to resample this for some more resolution. So drop in a resample after the add and display that. And it might be a bit hard to see in the display, but now we have more resolution along the lengths of all these lines. So now with that extra resolution added, let's drop in an attribute noise and display that. And this defaults to noising up the color attribute, but we just want to apply this to point position. So change the attribute name to P. Set the range to 0 centered, and this is looking pretty extreme right now. We don't need that much distortion in the shapes of these lines, so let's dial this down quite a bit. I really just want to get a bit of breakup on these lines here. So this amount of breakup is looking pretty good. This could work reasonably well. It's just a bit more wavy now, but I'm going to lower the element size a bit just to get some more detail in there. So this looks pretty good. And now let's set some density values on these points like we did for the shockwave setup. So I'll drop in another attribute noise. And we want this to just be a black and white value. So instead of a vector, let's make this a float color attribute. So it's just a single value. And I think the element size for this noise is actually working reasonably well here. And for the range, instead of the default positive range here, let's set a min and max. So I'll say the minimum density is going to be 0.2, so we're always getting at least a little bit of density in there. And then the max value, we can make a bit more dense perhaps, and turn that up to 2. It doesn't really matter if you leave this at 1 or 2, and you can always set additional multipliers on the Pyro solver when you're adding the density to the sim, but I'll just try this 0.2 to 2 range here. And just like we did with the shockwave source, let's now rename the color to density. So drop in an attribute rename that from CD to density. And if you prefer, you can use the visualizers to show the different attribute values in the viewport instead of just swapping between a color attribute and density. You can actually just display the density with these visualizer settings, but just using the actual attributes is the way that I'm used to doing things. Either way is fine. I'll rename that attribute rename to CD to density. And when we worked on the shockwave setup, I only briefly mentioned the temperature volume that you can use to control buoyancy. We didn't really mess with it in the shockwave because the buoyancy behavior was working just fine as it is, but generally in order to work properly, you need to have a temperature volume being added into the sim. So in addition to our density attribute here, I'm also going to create a temperature attribute. So I'll drop in an attribute create. The name will be temperature. It's just a point float attribute, and then we can set the value to 1. And now that we have the density set up and the temperature, and we have the velocity on there as well, we can use our volume rasterize attributes to create the volumes based on these. And then on this volume rasterize attributes, we can select those 3 in this attribute drop down here. So we want density, velocity, and temperature. And just like we did with the shockwave simulation, you can ultimately link the voxel size to the PyroSolver simulation settings, which of course we don't have a PyroSolver set up for this just yet. So you can feel free to leave this on this default voxel size of 0.1, unless you're working at a different scale than I am. In my case, my input is about 20 units or so across. So when I create volumes based on this default voxel size of 0.1, that took about 5 seconds to generate this, and it's not terribly heavy. If for some reason your input is much larger or much smaller than mine, then you may need to adjust your own voxel size accordingly. And for my final version of the simulation, I believe I used a voxel size of 0.08 on my PyroSolver, so I'm just going to set my source to that now. And things do look a little bit crazy and blocky in the viewport here, and this can be due to a couple different things. So currently this is displaying 3 different volumes on top of each other. So it's displaying the density values on top of the temperature, on top of the velocity, and even the velocity alone can look a bit weird when you just look at the voxel representation of that. Oftentimes, I really only want to see the density in the viewport, so I'll drop in a visibility. And the visibility SOP defaults to hiding the selected primitives. So in the drop down here, we can select temperature and velocity and then display that. So that's toned down what we see in the viewport just slightly, but it's still looking super blocky because on this volume rasterize attributes, the particle scale isn't set correctly. Now, if we had a p-scale attribute on here, which can be generated in some sourcing scenarios automatically. For example, if you use the Pyro source SOP, which can be useful to just fill a volume with points, then this will automatically set a particle scale for you. So when you're doing things like this, you may have a good p-scale attribute existing on your input, but we don't really have a p-scale attribute available since we set up this really customized source, which means we have to dial that in via this particle scale parameter here. So we need to turn this down quite a bit. Turning that down to 0.15 is looking a whole lot better, but I think we can get even more accurate. Yeah, turning this down to about 0.07 is giving us a pretty accurate representation of what the sourced density should look like. So now that we have our sources set up all nicely, we can go ahead and cache this out before running this into the PyroSim. For the Shockwave sim, I didn't bother to cache out the source. I just ran it directly into the simulation because the source was pretty quick to calculate. However, this destruction dust source is a little bit slower. It's not terribly slow, but it's slow enough that I might not want this to be calculating on every single frame. So I'll drop in a new file cache, point this to destruction. I'll make a new dust source directory, call that dust source.dust $f3.bgo.sc. We can just let this save out the entire frame range. So I'll turn on load from disk and then save to disk. So that didn't take terribly long to cache out this dust source. Took about 6 minutes on my machine here. And I'll add in a null after this, just in case we need to reference this later. Call that source dust. And now we can move on to creating the collision volumes and running the simulation.